What's good, guys? Today we're going to be solving design, add, and search word data structure. Okay, so I never seen this question before, but let's go ahead and solve it blindly. Okay, it's going to be a blind solve. All right, so first of all, the thing that comes in mind is I have to use a prefix tree. Kind of one of the things where you have like a root, which is, oh, it's not writing. Okay, hold on. Okay, kind of one of those things where you go ahead and just have a root. I'm going to say this is the root. Right. Okay. So we should be able to add words to the data structure. Let's say if we have a word, so we have something called like add word. And we want to add the word like cat. Right. What we do is we search if there's already a C in there. In our data structure we don't. So let's go ahead and add C. And from there we go ahead and add another word called like another letter A, and then one T, and that satisfies adding the word add word. So I think that checks out. Next is bool search word returns true if there is any string in the data structure that matches word or false otherwise. Word may contain dots where dots can be matched with any letter. I don't think they even care. So like if I was to put the word CA, if I want to say search CA, search and then CA, I think this would return true, right? Because it's saying any string in the dictionary that matches the word or false otherwise. By match, it means like, it doesn't have to be the ending, right? Can it be a prefix? Let's go look at some examples. Um, I don't know, whatever. I think that's not the point, but I think it should say true, right? Or maybe not. Okay, let's see. Okay, so let's say is going to return false. Whoa. Day, bay, may, but say is false. How about a? What? Hmm. Um, I'm gonna say, I think CA. I don't know. That's an edge case I'm kind of confused about. I think for our case, we're just gonna say this means if we put search CA, it should return false. I'm just gonna say it should return false. Oops. It should return. Oop, where'd it go? Okay, I'm gonna say this is gonna return false. Right, because CA is a sub word, not a full word, right? Because it doesn't have the ending. We'll tag something like end. Okay, let's go ahead and solve that. I think there's another thing, this little symbol, or if we see this, it means we could go ahead and add any word. So if it has something like search, um, CA, and then like dot, that would work because that'd be C is right here, A is right here, and dot means anything could run, so that would be T. Okay, let's go ahead and think of this data structure. First of all, I think we have to create a node, a class called node. Let's go ahead and add that. So I'm gonna name it node class node. Let's say node is gonna be a define init, and this is gonna be our constructor. And our constructor will hold something called is last word, this last letter, and initially it's gonna be false. What else do we have? We should have children. Oh, actually, we gotta put self. And let's put that into a dictionary. Now, by initializing, we want to just initialize the root. So root, I'll say self.root is going to be equal to, it's going to be equal to a node. Is there anything else we have to initialize? No, probably not. Okay, now let's go ahead and add word. So we're given the word and we want to add each character to the word. So let's go say let's say for letter in word. What do you want to do for each letter? We want to go add it. So I'm going to say, first of all, we're going to have to add current, right? What are we currently working on? So we do current is going to be equal to, let's say current is equal to self dot root, right? Because we want that root. Now we got to check the child's. Okay, if the letter is already in, or if the letter is not in, yeah, if the letter is not in current dot children, then we want to kind of just add it there. So we could say letter is going to be equal to current. Oh, actually, I would say current dot children at this letter. So this letter is going to be equal to a new node. And then we want to, either way, we want to go ahead and go down the tree. So we could do that by doing current dot, just current is equal to current dot children at this letter. Okay, we could go that, and that would be inserting the word into this. Okay, sounds pretty good. So let's go ahead and walk through that. Let's say we made our root. So we initialized our root. Let's go ahead and use a different color. I want to use a bright color. Let's use something bright. Okay, so this is going to be our root. Right, okay. So current.self equals root. So this is going to be current right here. And first of all, we look at a letter. Okay, let's go give it a word. The word is going to be cat. Right. So for letter in word, so the first letter we see is actually C. And then let's see. If the letter is not in children, which it's not because the node is empty, then we can say current.children letter is equal to node. So we go ahead and point this into C. That's basically what this is doing. Okay, and that's in our dictionary. And then now we go ahead and move our roots. So this is going to be our new root. This is our new current. Now we do the same thing. We add A, add T. Okay, it should be good. Now we're actually searching for the word. Okay. Now we actually go ahead and search for the word. Let's go ahead and do that now. We could do the same thing. We say current is equal to self.root. We could say for each letter in word, but now we're just checking it, right? If letter not in current dot children, then we could just return false, right? But then remember that we have a condition where if we see that dot, if we see that dot right here, this is the universal, right? Which means that any letter works. Oh, also we have to flag it. We have to flag the last letter. I forgot about this. So after we do that, we could say current is equal to current letter. Now we could exit that loop and we could say current dot is last, what is it called? Is last letter, and just equal that to true. We could add a check where it's like if, how do you exit a loop? If letter is equal. Let's say if it's equal to that one dot that we were talking about, is that dot right there. And then we should add a condition where we don't really care what that letter is. We go ahead and just increment current. Okay, so for example, we're going to have a word called dot A-T. So we don't really care what this is right here. Let's say we have another one, bat, B, A, T. We're gonna have to figure out which one to go down to. Damn. Okay. So you have when you have a dot AT, these both of these work, and they both will return true. I guess we could split into two other ones. I see how this gets difficult right here. If we pass it, we just look at A's. We want to look at these two. How can we do that? I guess we could do it for each children. Yeah, for each children. What if we have something like this? Dot dot T. So anything so 3-letter word that ends in T. So you look at C, we look at all its children. It only has one, so we'll go to that one. We look at all of their children, and then it ends with T. So we do the same there. It could be nested many times. Okay. If letters equal that, I want to say that current dot children. I want to say we could kind of use like a Q or a stack. I don't think it matters. We could add everything to a stack. No. We should go by stack. Ooh. Oh shit. For each value in, how do I make it nested though? Ooh. I think I might have to look this one up. Am I even using a good thinking solution? Yeah, I'll look it up. Index current node. Yeah, okay. Let's go ahead and look at the solution. Was that similar to this? Oh yeah, similar. Oh shit. Is that the same as that? Yeah, okay. So I gotta work on my recursion game because I knew that I had to use recursion, but to implement recursion was a bit confusing for me. There's no faster way? Okay. So it says define a helper function. Okay. Yeah, okay. So I'm gonna define defer search. And what do we give it? We should give it something like like letter. Oh shit. Index and current node. Oh shit. Wow. Huh. Let me go look for the solution that he gave before. I'm gonna try to understand it actually. Index and current node. how he's doing it? Okay. Okay. Hmm. Okay. Okay. I still don't know what we're gonna give current node, but okay. For I in range, index to length of word. Okay, let's see what depth first search. Did we give it 0? Solve that root. For I in range. Okay. Hey, oh shit, I just want to copy it. For I in range, char to match word I. So I go for branch node in cursor, the values. None of them eventually led to a completion this bad. Else. Wait, where's the stack in this shit? Char to match word. Char to match. Hey, where's the what's this line of code doing? If char to match is equal to, okay, char to match, what is this even doing? Char to match is word I. So word at that index is that character. So this is to go through every single character. Yeah, it's to go through every single character inside the word. Okay. We go through every in the node via index. Okay, so we could do that for index in range. Ah shit, we can't use index. For I'll just say I guess. I don't really like naming stuff I, but okay. For in range index. So we start from 0 and we go to the length of, I guess, the word. Okay. And then we could say current letter is going to be equal to word of that I. And I think that should be good. And now we should just go ahead and check if it is in there. So we check that I and we see if current letter is going to be equal to, if it's equal to that one thing, which is the wild card, then we go ahead and implement something. We could kind of skip it I guess we could say, what's the word? How do you skip? Is it, oh shit. Oh, we call it itself, right? For branch node and cursor. For branch node and cursor, that was cursor. Where did I use cursor? Oh shit. I called that current. Oh, so I'll go through all the values. Okay, so we get that branch node. Okay, let's collect the values. So we do for each branch node, we check out that branch. Now we call recursion on it, right? We could do def first search on index plus 1. Oh, actually, I don't even think we call it index. We just call it I. Or give it index. We're gonna the next word. I'm gonna say I, bro. Yeah, right. And then for the next one, we could just give it a. We have to give it the current node. Well, the current node is going to be. Um, hmm. Oh, okay. Def first search on the first I. Yeah, because we want to skip it in the current node. It's gonna be branch node. Why do we return true though? Oh, because it keeps on calling on itself. Yeah. Okay. And if it's not that, then we could just run the regular. Which the regular thing would be regular. This assumes that it is not a dot, aka the wild. We could just run the regular algorithm, which is saying that if, oh yeah, then we could just go next to the next one. If current letter is equal to word, no, if word I. Ah. If current letter. Huh. I'm gonna say else. Yeah, this is the one I was looking at. Right, and then say. Oh yeah. Current dot at word I, and then just return. No, you gotta get outside that for loop, right? Return true. Return current letter. Return current. Return is last letter. I'm gonna say, yeah, okay, that's it. Oh, we want to call def first. Call it on 0 and call it on word. Call it on root, actually. What's this? If we checked every branch and none of them eventually led to word completion, this path is invalid. Okay, this should be good. Yep, and that was it. I kind of just had to remember what recursion was. That's why I'd look back and forth a couple of times. I think this kind of explains why you should practice LeetCode, I guess, every single day, not just practice it a bunch and take a break. Because when you do that, you'll run into problems like these where you kind of know the solution and you mapped it out, and like you're not able to code it. Yeah. This is a little fun question. I want to try to solve this again in the future as I practice more recursion. But yes, that is my solution for design and add search word data structure. Thank you guys for watching.